Okay, welcome back. Some of you might have wondered what these sticky notes are for. So this is basically a way for me, as I said earlier before the break, to collect feedback. And again, yet another time, I have to say that this was very important because it gives me a handle on to see what you understood and where I should maybe repeat something. So let's go through it real quick. A couple of people were mentioning that I was too fast. Yes, that's always a problem. I'm happy that it's not more than the majority of you guys, but I take this as an advice to slow down a little bit. Um, People wondered connection between two caches. There, I don't understand what this question is targeting. These caches are on the die. They are right next to the arithmetic units of your CPU. The square thing that is inside your laptop. That's the CPU, and on the die there are these memory caches, and they are connected by a direct connection to the CPU. Did that answer your question? Because I myself, I don't make these chips. I have to say, I cannot tell you in detail what exactly the connection is. If someone wants to Google it or then put it on the Etherpad. Or maybe this question was targeting something else. Who actually asked this? If you want to speak up and ask or rephrase the question, this would have been your chance. So very last test, not fully clear. I will come to this. This I don't understand. People don't like Emacs. Yeah, aha. Grr. Missed some command not visible later. Yeah, okay, I understand this. This is always the problem with the screen. That I have to take note how to maneuver it. If you want me to scroll back, just yell at me, okay? Or just say it politely. That's also an option. Not really clear what training data is and what the for loop does. Okay, we'll come back to this. Too fast, we did that. Not sure if I can implement testing in my code. What do you mean? Is that a problem of your code, or I really would love to hear why you put this, the individual, because this is an important point. Because the question is always, what does it mean if you cannot implement a test? Is it a problem of your code, meaning that it would be untestable, meaning that this would be a really bad thing from a software engineering perspective? Or what does it mean that you cannot put tests? Is the build system too complicated? You simply don't know how to link in the tests. So whoever asked this, feel free to approach me. I can also have a look if you want. I cannot promise that I can help, but I can have a look. Point about memory cache was too fast. We come back to this later. I didn't see the connection to the coffee machine. Okay, I give you 2 hints. There's an island in the southwestern Pacific. Yes, it is. A lot of coffee comes from there. And this island has the same name as a programming language. It has 4 letters. I think that's enough. So I don't want to bash any Java or so, but I always hear this when I talk to scientists that use Python, Java, higher level languages. I don't care about the details. I just want to get my job done. Yes, that is a valid point to make. On the other hand, if you do something that is really performance critical, maybe you should revise your attitude towards the architecture of a computer. Okay? Maybe it's important at the end, but only, mark my words, only where it's performance critical. I don't want anyone start off learning programming in C++, for example. Why should they? There are much more easier languages out there, right? So it's an important point, and that's why I actually called it the coffee machine, because we actually passed because I also had a lot of discussions with my colleagues when I was at PhD. Why must it be so complicated? It's because the CPU and the laptop itself is a complicated thing, and we reached a point with this example where maybe it's worthwhile to invest time in learning this complication. Okay. So this is why I make this joke about a coffee machine. Coffee machine is something that you just press a button and it works. Okay, and obviously here this is not the case. Problem to see the screen, hard to follow, yes. C++ iterator, C++ 11. So what were you up to? C++ 11 iterator. I don't know who wrote this down on a red piece of paper. Funny, nobody wrote it down. But I have it here. Yeah. The range-based loop. Ah, okay. Yeah, that's C++11. True. So this is a new style of writing a for loop. I just wanted to mix in some new stuff. That's all. Just so you just be exposed to something else than what people regularly use. Green. So that's really quick, and then I will cover the cache memory thing again. I was awake the whole time. Excellent. That was actually the best screen. I mean, this is what a compliment. Okay, good. People surprisingly like perf, which is nice and was not by my intention. Cache internals, Google test, a lot of people liked, which is nice. Optimizing code, good style. LSCPU people liked, which is also good. Etherpad, yeah, I know it's a really nice tool for learning and exchanging ideas almost in real time. Idea with speed test with simulation. We'll get back to this. Unit testing, people liked interactivity. Thank you. Chrono and check for performance and everything. Good. So so the bottom line, what I understood is that 4 to 5 people out of you guys didn't really catch what the idea between the training data and the problem was. And I would say it's normal. Okay, when I first ran into something like this, I also didn't understand. So don't feel too upset about it. So let's look back just really briefly. What's going on? So here's our count active method. Okay. So let's look at the implementation again. So what's the problem here? We have 2 loops that go basically that just ask for the value inside an array which is accessed with this function. Okay, I will bring up the implementation real quick. I cannot promise that this will help you to see the implementation, but okay, let me increase the font again. So what's this one? Okay, this is what active devices does. You see underneath, active devices just probes this vector int, which is again a one-dimensional array. But it does it in the wrong way, right? Because underneath the API that we are using, they also just use one-dimensional data structures, which is totally fine. But they need a way to actually translate the coordinates of our room, level number and room number, to the position inside the array. Okay? And the only mistake that we did was to use it in the wrong way. Okay? I basically played around that I copy and pasted this code, and then, if you remember, I copy and pasted this code, and then just inserted one line. And this line, it's way about now, sorry. Ooh, this was too fast. And this line makes all the difference, because the levels are basically, I have the thingy, the figure here. Coming back to this illustration. So this is, for example, one level, right? These are the individual rooms, aka integer numbers. Okay? So our for loop, so let's look at the for loop again. So what it does, it first goes through the rooms, then through the levels. So as I said here, first iteration, R is 0, L is 0, this item. L is 0, I'm at the wrong place again. R is still 0, but L is 1. That's why I'm here again. And then etc., etc., etc. Right? So this is what these 2 loops do. And this is a problem in terms of performance. This is why we created a simple 1D array to just have a reference data structure that we can test performance against. Okay? Which is always very important, because APIs can be involved, they can have much more difficult data structures beneath, you don't know. That's why I always think, oh, why not just take a vector, something very simple, and test our algorithm against it, if it's possible. Yeah, and then we basically changed it, we just ran through it one by one, And this is what then happens. So you take basically level 0, R0, level 0, R1, level 0, R2, etc., etc. And this way, you basically remain inside the cache line that was just loaded into your CPU's cache. So this was the idea, whole idea about it. What basically is now left to do, and which is the easy part, to simply change these two lines. That's all. You simply, that's why this is sometimes a very common mistake, because it's so easy to make. Okay? And now it's correct again. Now if you would run this, you should actually see almost the equal performance. There's only one difference between the one-dimensional case and the two-dimensional case, and this difference is this branching here, this condition, which makes it a little bit more slower than the 1D implementation. Okay, good. Thank you for providing the feedback. I will try to basically, I would suggest that we work an hour again on the next lesson, and then make a small break again, and then finish up the day until 10 to 6. Okay, because we still have an evening talk, and I don't want to get you too tired, if possible. Okay, so let's go to the, how do I see? Let's go to the next lesson. So thank God I have these links here, so I don't need to go back. So we go now to data structures galore. Okay, and this is now the next lesson. All right, so again, you simply have to change the directory. So there's directory 0.2 or 02, fast and slow inheritance. Even wrong name. This was my old name. Forget the inheritance. We don't have any inheritance in there. And again, so there are a couple of header files that we will read later on. And just open test start underscore here, compile it, run it, and let me see by a green sticky note that you hopefully have collected by now. Do you guys need new ones? Then please distribute them. There is an entire stack. So I will do the same. There's a failed test. Yeah, of course. This is stupid. Sorry. The obvious. Come on. Yes, I want to save you. Good. Okay, so sorry about this. There's a small mistake in the test in the start file. Please correct this, so that I should have just copied the old one. This was a typo of mine. Sorry. Okay, so this is how the test should look. So please compile this in this way, and then give me a green sticky note once it's running. So there are some red ones. I hope this is still with the old version. Yeah, this is still with the old version. Please change. Yeah. Well, let me increase the font again. I mean, it's really small from back here. So always tell me. Is that better? Why didn't you tell me? Okay, so in the future, if I forget to increase the font, just let me know. Okay. So let's put the output window down here. And let me update my notes. And then we are all set. Okay. So we have a lot of green. Okay, good. So what's the situation? Now, basically our friend Lola Likely, she's now been tasked by a different person, namely the head of the institute, has approached her. And he said, Lola, I've heard about you. and that she's doing a wonderful job in the IT department, and he has a special task for her. Her program is supposed to run on a dedicated screen in the foyer of the institute, so that when people come in, basically they see immediately how many devices in-house are active, what temperature they have, what power consumption there is in total, etc., etc. Now, if you hear this, you will immediately say, okay, so if this is real time in the sense that a human cannot distinguish that the values are actually, that they're lagging behind, that actually has some performance implications. The code that actually generates the data and it actually renders the numbers should be pretty fast, right? Obvious. So now what she basically is tasked to do, to simply use the existing API, which I have here pasted and which is also inside info.hpp. I will open this now, info.hpp, and she's basically asked to use this as much as she can, because the boss of the institute is worried that if she would write everything from scratch, she will lose time, and he wants to have it as soon as possible. As always with bosses, right? So this is basically the API. I will show you the API real quick, and then we will work with it. So every device, this is something that you see here, is simply symbolized by a structure. People that are now reminded of C, they are somewhat true, somewhat right. This is for me just at this point representation of each device, and it doesn't need any methods right now. We will add this later. Okay, so the problem is for rendering and everything, I mean, this is basically available in memory. So this is what you can have access to see if each individual device, what temperature it has, how much power it's consuming currently, and some information about the network protocol. I just came up with this structure simply to mimic something that one would use in real life as well. What she's basically doing, or what she will do, again, she could, as we just did, write a test to actually see if this API is fulfilled. But she has access to all these device information by means of the device info object. So this is just a vector of these device underscore t's that we just saw. It's nothing more. Okay, so this is just a large vector of these device objects, and that's about it. Okay, now let me see. Yeah, there's already been some work done by her predecessor for displaying the actual values, because what she has to do, she has to prepare the display somewhat. Okay, let's open the render entity and let me increase this. So there is render entity. So this is supposed to be an abstraction of the two values that are most important, namely the temperature and the power. Okay, and how this is done is very common from my experience for object-oriented frameworks. Namely that these basically simply capture these values and then abstract the individual logic away. So you see here there's a dedicated class or structure which we will have a look at in a minute for the temperature, and there's another one for the power, which makes sense a little bit. I mean, they have different units. You could do it like this. The rest of the class is basically straightforward. There's a default constructor. There's a copy constructor. I'm using initialization lists. So far, so good. Nothing special. And then you can have access to the individual subcomponents, right? So there you get a pointer, const one, to the underlying temperature. I don't know. Do you guys know this symbol? So those ones that just nodded, what is this? What does it do? Say it loud so that everybody hears it. Yes. So this is simply, it returns the address of the member field called temp. Nothing more. And in effect, this is a pointer. Okay? In the real sense of a pointer. Not a pointer to heap, but it's just a pointer. A pointer somewhere to memory. Okay? This is a small trick. It's a dangerous trick because you should always be aware how long temp lives, because as soon as this is out, this is destroyed, the pointer that you give out is invalid and will give you a seg fault. All right, so that's why I'm saying use this with care. But I mean, Lola just took this. Okay, this is how it was. All right, so this is the situation. So let's have a look at these views. How they are structured. Here's the temperature view. You basically see that the value is captured. Some HTML string is generated because the actual display will be done in HTML. Then the value of the data is prepared. So here's a conversion to a string, and that's about it. Okay. So the temperature view is simply a small container function, a container class, if you want it. And it has basically just a constructor and this one method called prepare. Because what they need to do before inserting some values in the screen, they need to calculate how wide the value will be. Okay, this is just a setup that she has to work with. One word of warning and caution and hint. Some people might have noticed that I use structs. What is the difference between a struct and a class? Say it loud, please. Yes. So I'm just ditching all the encapsulation rubbish. Okay? Just to make my life easy. If this is something you would like to adopt, depends on your situation. Okay? It's really, that's why here in this context of teaching, it's totally fine. And to be honest with you, I'm using this actually in some libraries as well. But only as long as I know that I'm very far away to the API I'm giving out. So that's why I'm saying it's very context sensitive what you use. Okay, so not that people come, he's not using object orientism right way. Okay, so this is the situation, and what she has to do for the starters is, for example, again, sum up all the temperatures and sum up, for example, all the power that is currently consumed because her boss wants it to be displayed. I'm sorry, not sum up the actual values, but sum up basically how many characters need to be reserved. So this is the strange, but this is the task that we want to do right now. So what I'm going to do, I'm rename this small file to, what should I rename it to? Test prepare on screen .cpp. Okay, so let's start. So what we want to do, we simply want to see if render class works as expected. So we write the test again. This time is a different type of test. Those of you who are well awake, as you told me, see that there's two characters I have introduced. This is a so-called test based on a test fixture. So a test fixture is simply something that is called or constructed before the test is actually executed. So this will basically help me to always have the same initial conditions. Okay? So this is a very common technique in unit testing, to have a test fixture that you hopefully do not have to alter very much and that you can base everything on. Okay, so first I want to create a vector of these render entities. We call it current devices. We reserve some space. and then we simply want to copy the data. Okay, so we do a const range-based for loop. This time with constant references, item, whatever. Sorry, you are completely right. You can have a look at it says render entity up here. So that's probably the name. And then we want to do something like this. What do we check for? We check for, I don't know. Anybody has any idea? We want to see if the pushback actually worked, which is close to being a very silly test, because we are testing the implementation that we have up front here rather than actual logic. But bear with me. So we're taking the first item, and then we take the temperature. And then we could just look at the data and say that it's supposed to be greater than 0. Let's say, because if something is on, it should have a temperature. Exactly. We could do this test. We can also test directly if the temperature string actually has some size, because this is the functionality that we will use later on. So why don't we just do this? Because then we have two tests that actually should go through both. If they don't, there's a problem. So this is, I will, in a minute, after I gave you guys a chance to actually write it up. Is it, please tell me. What does it have? Then its value. Yeah. That's true. Go tell the author. Of course, it should be a float, but for the sake of explaining it, I think it's okay. All right, so let's come. Of course, not start here. Prepare on screen. That's our test. So apparently, it takes quite a while, because there are a lot of devices. So this basically means, so this is always something, it's passing, which is good. And so this is a very common situation. That's why I provoked it, because this is always a big problem when you are looking into performance of things. You should have enough items or data to work with to actually make a meaningful test. On the other hand, what you want is a high turnaround. So waiting 11 seconds for a test to come back is annoying, because then you are sitting here waiting 10 seconds, then you can continue, then you have to compile, and then you wait again 10 seconds. So it would be better if it would take less time, but I think we can do it. Yeah, why don't we just do it? We should cut it in half. The observation should be the same. And then the problem is, if we do this, this whole thing breaks down. So we have to replace it. Ha ha. But it's a good advice. Um, See, this is one of the virtues of pair programming, even if it's you, the crowd, that look over my shoulder. Because these kind of things are spotted immediately. Okay. Launch it again. Should take. I introduced an error, of course. Pushback, blah blah blah. Item was not declared. I know. Come on, you should take half as long. Good. Now it's 5 seconds. You can basically put it decrease the time it takes as much as you want. Oh well. But let's continue for now. So just use an arbitrary number of items here. But for the real measurement, the actual size needs to exceed a certain limit, so that the demonstration hopefully will go through. All right. So the problem now is there is actually a problem. Let me pull this up just to get you started on the. Yes, so we are here basically, and I want to have this illustration. So render entity, this vector. Okay, why don't you just finish, put up a green sticky note once you're done with the test, and it runs through, even if it takes 5 seconds or so, and then I know that I can continue. Maybe I'm rushing too. People told me I'm too fast, so I should slow down. Yes. Okay, so what do you know what size T is? Does anybody know what size T is? So an int is clear. 32-bit signed integer. Size T is basically the integer type on your architecture that you are compiling to that has the largest unsigned width. So typically in loops you should use it. Size T. This also is now in the standard. So there's also a std or standard size T, which can. So this works as well. Which can compare equally to standard int max underscore t, which is really the largest integer that you can have. And I think it's even a type def, but I'm not sure on this. Typically, I'm basically used to using this in loops because it's just much more safe. If you ever have more than 2 to the 32 minus 1 item. If you don't, then you can use int or short or car, depending on how many items you expect. Okay? But yeah, thanks for the question. Okay, everybody has a green sticky note. Then I could continue. And we can proceed hopefully until the break. Okay, there's still one pair over there, which is missing. So there's also still someone typing. Just tell me if I don't need to wait for you, let me know. Otherwise, okay, there's still people working over here. Grün. All the tests should go through. So on my machine, they do. With my code base. And for them as well. Okay. Okay, because I would like to continue doing the actual task that she wants to do. Okay, should I just go? Okay, good. Put down the green sticky notes. Then let's continue. Because so far we've just looked at everything works. So now let's sum up letters needed. So we basically can leave this as is right here. We can ditch the asserts. We will just reuse this vector of render entities. And what we would like to do, as I said before, we would like to sum up the number of characters that each individual render object requires, or each individual view object requires. So again, for int r equals 0, we have to insert a number of repeats. And repeats. This will of course fail because I didn't define repeats up there. I will do this later on. And then the number of letters can be quite high. So we could stay with size t. How did I call it? N letters temp equals 0. And then we also want to have the power. And now the rest is basically straightforward. We temp, no, we call it n letters temp plus equals, and then we take current devices I, and then take the temperature view from here, and then call the prepare method. And we can copy these two loops. And do it like this. Let me increase the screen a little bit so that you can see what I did. So this is the full function. Of course, this is a little bit error prone, what we are doing here. As always, when you just rush and code, this is a little bit better. Or if you guys really want to do C++11, then you could also use a range-based loop. Yeah, because up here we are limiting the entire current devices to half the number that we actually can get for training. And then, yeah. Okay, good. Then add some assertions. I think by now you should actually have a notion of what to do. This is a precaution. We have to reset our counters for every repetition. Let's see if that still fits. Probably not, almost. Let me just add one test, and I hope you can fill. Sorry. Okay, let me add in one test. Maybe the power, I don't care. Something like this. Good. You should by now be familiar with the structure and why we do this, why we repeat the experiment multiple times. Again, Lola is in a situation that she knows that the runtime of this operation, namely summing up the number of letters, is important. So she wants to invest time and learn the performance of this. Yes, we did forget that. That is true. So please do that. But I don't want to so why don't you guys just compile it And once it's running and giving you a green light, then please put up a green sticky note. Bless you. So we have the first green sticky notes over here. Take your time. I want you to finish that test because we will use it as a measurement basis later on. I could play. Yeah. Thank you that you ask. So why would I do it this way? I could also use the postfix operator, so R++. For an integral type, this is of no difference, right? For a non-integral type, everything that's an object or iterators also, you should always use the prefix operator because it does not do one copy that the postfix operator does. Because what this does is add first, then return the value. That's the prefix, right? That's why you put the plus up front. And the standard way how to implement the postfix includes an additional copy that I don't need, right? And look it up. I mean, I once did it in a training and just implemented these postfix and prefix. Incredible how hard this can be to do this right. But C++ requires you to do it in a special way. This is a feature language. Good. Green nodes everywhere. Splendid. Then let's continue. I mean, you guys obviously had it running. So I'm going to do the same. It will take some time. And the question is basically now, what takes the most time? So what we do now is again implement or use timers that I have to catch from the other code base. I'll go away. And you will basically see that, let's do that real quick. You will basically see that we again do auto start. So you can now copy this timing, you simply copy from the other code, right? I mean, just take the code from the last lesson and just copy it in. Standard chrono high resolution clock now. And we do this at the end as well. I forgot to define the repeat. Static int repeats 10, something like this, or let's do 5. It doesn't. Aha. Good. Splendid. I did prepare well. All right. So now we have to do this ominous double time diff microseconds equal. Now you can need to help me. Standard chrono duration cast. What's next? Standard chrono? No. Standard chrono microseconds. One word of caution, since I'm among physicists, I like to have the units inside variable names. Simply so I don't forget. Okay, and simply because it means that I need to be careful not to change this unit somewhere without changing the variable. Because if I want to reuse this, I immediately know, okay, this is in microseconds, right? So just a tip. Count. And then we add another test that we are sure that we run that we actually consume time, which is always good. All right, we can actually run it, and while this is running, I'm preparing the output, because we will now come to the point where we say, why is this so slow? Because it actually is slow. And what you will also see in a minute, what the actual, because the test timing is actually reported by gtest. Where is it? 10 seconds here roughly, 9.6. But the question is how long our operation is taking, not how long the entire test is taking. Because we also do a lot of boilerplate on top. So let's see. It runs through. So take down your green sticky notes, by the way, please, so that we are back to 0. Okay, so 3 seconds, roughly, right? We have to divide by repeats, something not to forget. But that won't change the result. Okay, good. So you already see that there's some overhead here. So the actual work lifting is done within 3 seconds, and the entire test takes 9. And this is simply due to the fact that we do all this pushback stuff on top. Yes? Yes? Yes, exactly. And this is also the reason why I didn't do it. Okay, good. Now, why is this slow? I can tell you it is. We will do an experiment in a minute with some synthetic data again. Why could this be slow? Does anybody have an idea? Because I can tell you, you might wonder by now, so why are we doing it this complicated way with all these structs inside structs? Because in object-oriented code, this is often the case how you find it. Either the sub-objects are part of, for example, this render entity, or they are just pointed to by a pointer simply. So this is a very common practice, and the reason for this is actually why people do it this way, to basically keep things separate, which is a good idea, right? Because now in the setup that we have currently, you can test temperature view independently from power view, I called it. So that's all fine. And then we have a mother object that basically just encapsulates the two, and this is the common interface. But this is a problem in terms of performance. Does anybody have an idea? If not, I will just try to explain it. We can also just write the test and see that, and I can prove you that it's much faster in a different way. Shall we just do it, or shall I explain it? Test? Who is in for testing? For more testing? 3 people. Okay, sorry guys, you're the minority. So what's going on? How is our vector laid out in memory? This is basically what's going on. We have, did we call it, current devices? Standard vector of render entities is called current devices. In memory, it looks like this. Okay? I skipped render before entity to keep it brief. Okay? Just don't confuse. So there's the first object, second, third, fourth. Okay? So far so good. That's what we did with all this pushback at the beginning. If you look inside, it looks like this. First, there's an item called this. Who knows where the this pointer is? Pointed to what? To the current instance of a class. This is something very common. This is something at the heart of C++. Okay, so C++ stores instances of objects in a way that you have the data members and always at this pointer. This is also the way that methods are called. They actually first basically do a method call, And the first argument is the this pointer, and then come the actual arguments. This is what happens behind the scenes. Anyway, so first have the this pointer. This is something you cannot elide, so this does not go away. Then you have this temperature instance, and then the power instance, right? And then next object, this temperature 1, power 2, etc., etc. What did you just learn before the coffee break? What should you not do? Yes. Because what happens if you loop over this is basically, for example, in my first loop, where is it? Think about what this does in memory. What does this do? So I'm simply probing the vector, nothing else. So I'm taking the first element, this is entity, and calling the this pointer. From there, I'm getting access to a temperature, it is, I think. And then I'm going to the next. So, so there you already see my two fingers. There's a distance. They're not next to each other. And performance-wise, this is a big deal. Because we, again, do not use the caches as we should be. Okay? So again, we make a step. We first go to this, then we go to temp. Then make a step, this, temp, etc., etc. And inside temp, and in these objects, they also have an elongation in terms of memory because they themselves contain data. Actually, they contain a lot of data because the standard string is a quite big object compared to an int, basically, right? Because it has a size, it has the pointer to the actual characters it contains, etc., etc. So the distance between these two is quite large. So we are throwing away cache space again. So let's make an experiment to see how we can accelerate this. Okay, so let me go full screen again. So we have to, for this, what we actually have to do, we have to do the preparation in a different way. Let me see how I did it in the material so that I'm staying close to it. Yes. Okay. So we can store this. We don't need. Oh well. Let me do it this way. Let me start from scratch. Always good to start from scratch. Some are letters needed. Some are letters, let's call it optimized. So what do we need? What we basically need is, as a preparation, a vector of ints. We want to reorganize the way how our data is stored in memory. So current power width, I called it. We again don't want to deal with the entire data. We just want to deal with the half of it. So let's do this again so that the comparison is fair. Okay, and we initialize with 0 just for the sake of sanity. And we do the same with temperature. Right? Now, okay, we do something that you should all have seen a lot of times. So we again go into a loop. And all that this loop has to do is extract the width, and this is now a little bit involved. Call current power width I equals standard to string, and now we want to have oh, I did it in a different way, but it's fine. Now I want to have IoT device info dot power consumption. That's it. Exactly. So I'm basically doing what this whole struct API beneath render entity is doing, I'm doing this by hand now, just for the sake of the experiment, just to see what performance I can reach. Exactly. So now we have this, and now we could now use the standard library for doing the summation. I'm not sure how familiar all of you are with this, so that's why I'm doing it by hand. But I encourage you to actually look into how to sum up a vector with a standard library only, because it will potentially make your code a little bit more readable. Because these raw loops, they are always kind of a pain. There was actually last year a talk by Sean Parent, a big C++ evangelist at Adobe, that actually gave a talk called No Raw Loops. Okay, and if this guy said, and his point he's trying to make there, I don't want to give it away yet, is actually a good one, something to think about. Although I have to say I always have a problem with these kind of general statements. Yeah. Say what again? The vector sometimes. Oh yeah, you're right. It's wrong. Very good. I forgot something. What we actually wanted is to get the size of the string. This is what the render entity object, well, actually the temperature view does. You can look it up in the info.hpp. I'm sorry. Very good. Well spotted. See, this is the nice thing about having code reviews. People looking over your shoulder. Or that you actually sit down with someone and say, hey, here I have a piece of code and can you have a look? Something we should do more often, I think. Anyway, so stop preaching, continue coding. All right, so let's continue. Size, we could make our life easy. The rest is more or less similar to this. Not copy and paste too much at a time. Okay, and let us temp. Then we actually do and let us temp plus equals current power width. No, we want, this is temperature first. It doesn't matter really. Whoa, what did I do? And temp, and we do the same thing for the power. Another rant about general statements. What I often see with scientific codes is large loops. So people would basically take this statement and put it in this loop. Yeah, you are obstructing the compiler. Be aware of this, okay? There are some very important optimizations that can especially be done with this here. And if you want to use them in the compiler, don't do it. Again, disclaimer, this is again one of those statements which are highly context sensitive, okay? I just think it really depends what you can and what you could do. But I can just tell you that current day compilers can optimize such a loop way better than a very big loop. But this also may change, etc., etc. Just a word of warning. Still one mistake, and let us pow, and then it should be, that should be it. Typo here. Yes, that's there. That's there. Looks pretty good to me. And then of course we finish with a time measurement and then with some tests. Ja, ich erst. So I'm also very excited. Let's see if we did something wrong. And minus start should go. We call this optimized. And letter power is also there. Time diff views. So again, compile it, and once you have it running, then please put up a green sticky note. I already have temperature. Temperature is not there. Maybe it's just temp or something. I found the first bug. Ah, of course. Okay, now it runs through. Okay, great. So please put up a green sticky note when it runs, in your case, and then we'll look at the timing. I'll just go like this so nobody sees. Okay, so, and then we're almost done for this section. Yeah, it worked. Yay. Say what again? Yes, sure. Okay, so please put up a green sticky note once you're done, and then please paste the results of the time measurement of the 2 loops only in the Etherpad, so that everybody can share it and have a look. Okay. Okay. I just spotted a bug in my lesson material, but anyway. So if you discover it, you can feel free to send me a pull request to the repository. But anyway, so put up a green sticky note once you're done. This section is actually quite far. Here you guys seem still to struggle. If you guys need help, just let me know. I don't want to. Ah, it's run. Are you waiting? Okay. And then feel free to start contemplating where the difference in runtime comes from. We actually discussed the answer. So let's see. Yeah. Yes. Some people always. Oh, this is. Where am I? Yeah. Yep. Guys, if you just put in time, nobody knows which time is time. Can you just fix this in your code? For time and time doesn't say anything. Yeah, there's an optimized time. Hooray! There you go. Yeah, so just say, I mean, I assume that I know what time you mean, but yeah. So splendid. I mean, I'm very happy. This turns out to be a very good exercise. Yeah. So we have green sticky notes everywhere. Oh, excellent. Over there, you guys are still looking, checking why it's not working. Oh, of course. Which portion of the code do you need? It has grown a little bit. Down. Maybe next time I put on a live GitHub repo that you can just git pull. We could do that. Yeah. Is that okay? Yeah. Good. So please put up a green sticky note once you're done. Then we can discuss what we just did and then close up this session. Okay, more green sticky notes. This, of course. You mean the beginning of the unit test? Okay. Are you, what kind of, what are you struggling with? Kelvin. Kelvin. The line is wrapped. Yeah, sometimes it's that easy. Okay, so I'm just waiting for you guys because I want you to have some numbers. Um, you guys in the back, if you struggle with something, just let me know. It's fine? Okay, good. All right. Getting there? Still not compiling? Getting there? Okay, I'll just assume that you have a green screen. Okay, so what's going on? Why is it so fast? Of course. Obvious. So this is a very common problem especially in in object-oriented codes. And the problem is that we stored our data in what we call an array of structures. And the hardware doesn't like this. What it rather likes is a structure of arrays. Okay, we simulated this with this last test now. We basically have two vectors which are contiguous in memory, and basically they're lying next to each other. So we actually skipped this. I just put it here for reference. It's actually out. I should actually remove it. And if we calculate the sum of all temperature sizes, we just go through step by step and thereby exploit the caches to the maximum. Okay? And this is why this code runs much, much faster than the other one. Okay? So when you go home, look at your for loops, look how your memory is laid out. It might be worthwhile. Again, I say it might be because it really depends. If you just have 5 items, it doesn't matter, right? Because they all fit in cache, done. But if you have thousands of items, then it may be a good thing to look into this. First, the girl in the back. So what did you do? Ah, okay. Ah, where is it? Time with 2 loops after another, time with 1 loop. Okay, so the compiler picked it up. Very good. And then optimized to even get lower. Very good. Thank you. Then you guys had a question or a comment. We'll leave this for dinner. Because the thing is, so I'm coming from HPC and I'm doing a lot of coding for GPUs. So we're using GPUs to accelerate a couple of things. And they're on these architectures, and you can actually say this also holds for the CPU. Again, if you're in a performance critical section. So again, so that everybody knows, in a performance critical section, okay? Then this layout of memory is far better for the hardware. This holds for CPUs because there's something called SIMD registers that you can exploit. And this also holds for GPUs. Okay? So once you want to work with them, better use this. Right? And of course, it will require you to refactor your code. This is basically what you're... Stefan.
Comment here is perhaps that having noticed that structure is a necessity, one can think about perhaps about clever containers containing your object. So just setting up the template library vector putting your object in results in the structure that's opposite to the perpendicular to the optimal. But I could imagine that one could design a templated container structure that sets up the memory.
Yeah.
When it receives an object of new type, disassembles it.
It splits it.
Access to the data.
Yes.
Stores the data internally in the container.
Yeah.
But when you access it from your code, you don't see that. So you don't have to mess up your design.
You could do
if
this.
you use a container that's optimized internally together with the objects that we're storing in there before we have to make some trains there. For example, to make sure that we can get inside there.
Yeah.
I think we can have both. At least you can try. Because I hear that quite often that, okay, we have to have an array of structs and so on, so we have to go away our object-oriented design and go back to C coding. And I don't believe in it. I rather believe in not just blindly making the template library vector, of course, then it doesn't work because but rather creating a thing, which is dedicated to the purpose and can probably, I don't know, with some traits also be shipped to the GPU.
Yeah.
Or have special methods that allow to be copied over
in
an efficient way to the
yes.
GPU. You don't see that from the outside.
Yes, exactly.
You really shield that from
yeah.
The users don't understand GPUs.
So that's why I said you have to refactor your code in some form or another.
And the effective way of approaching this problem. First, we try to design the code in the right way. Then, with the profiler, we try to understand where the bottlenecks are. And if there are significant massive bottlenecks, then you address these bottlenecks with proper solutions.
Yeah.
But never try to do performance optimization while doing the design of the code.
Yes.
The risk is that you end up with poor design and poor performance.
Or even better, you end up with wrong code. And I mean, wrong code which is fast helps nobody, right?
So this is to say that there are techniques to address specific performance problems, but they are not in conflict with this.
I actually heard it. I have to make that in front. I've heard serious people say, oh, finally, sort of, it's a relief. We can go back to procedural programming because the data structure is right. Okay, we can forget about the object orientation which we never understood in the first place. And I don't know. I mean, I like having arguments over coffee, but I've heard that several times.
Yeah. So I would say
make an exercise out of designing a container that takes care.
Yeah, we can.
For the purpose of
we could do that. Time for a break. I mean, we can continue discussing. I don't care.
I just then we need to implement the Absolutely. That is where iterator comes in because you want to be careful with how people access. You can't just go in. Well, maybe you can design a square bracket operator on the container that just picks up the data from the right places. Or an iterator that knows about all of this and then manages to iterate.
5-minute break. We continue 10 after or 11 or so, and then we'll do multi-threading. Okay.
This is really the good one. Finally, we kept going all the way. And
All right. So shortly after the break, we are going back to lesson number 3, and again, just as we did the last time, please open the test start here. What was this? Oh, yeah. And then try to compile it. Source index. Exactly. So this is called the free lunch is over, all just plain threads. Okay, let me do the same. By the way, who actually already heard this sentence? The free lunch is over. Does that ring a bell? Yeah, it's related. So the free lunch is over was coined by Herb Sutter. He's one of the C++ gurus at Microsoft. Herb Sutter. S-U-T-T-E-R. And what this basically means is that for a long time in the 80s and 90s, people and software companies basically did not at all look into optimizing the runtime of their code, especially with regard to multithreading. First of all, multithreading, well, the CPUs were hardly capable of it, and second of all, what they simply did was sit down and wait until the chip manufacturers would actually sell faster chips. So this is what is called the Moore era, where Moore's law actually still was holding up. Now we are in what is called the post-Moore era, so this time is long gone, and Herb Sutter basically with this sentence coined the end of it. So that what he wanted to indicate, I think, but maybe I'm wrong, is that we as developers have to sit down again, look at the codes that we write or have written, and look if we can make them run on multiple cores at the same time. And this is what we're going to learn in the remaining half an hour, and we'll then continue tomorrow morning. Okay? So just to give you basically a notion where we are. So we are lagging behind quite extensively. I have obviously prepared more than we can handle. And I decided to stay with the parallelization first, because both Maria and Stefan indicated to me that this is a valuable asset or knowledge for you to have. Because if you look at the Indico page, I also prepared some material for template brackets, meta brackets, programming. Okay, so I would stick with multithreading now and then see how far we go also towards tomorrow morning. Okay, you have green sticky notes up. All the tests are running, I hope. Basically, let me do this as well. I increased the font again. So good. So it's basically working, and then let me pull up my notes. This is number 3. The free lunch is over. All right, and I'm starting with the sketch I made, and we'll start with a non-code exercise. All right, so basically Lola is still our friend Lola is still tasked with writing this application for the Institute of Things. Again, we had this with we had the task in the last lesson that you should actually contribute rendering all these values in a monitoring service that is displayed in the foyer, and she's still looking into this. She showed her code to a colleague of hers, and her colleague basically said, well, you know what, as the individual devices in memory are independent of each other, we could actually do this in parallel. Okay, and this is the overarching theme that we will try to follow until the end of the next lesson actually. First we will try to, no, actually also until the end of this lesson. And so basically what her colleague actually shows her is this conceptual sketch of a CPU that you also have in your laptop. Here I took a CPU with 4 cores, as you all know. There are different types on the market with 2 cores only, with 4, 6, 8, whatever. But they in principle all have a similar structure. On die you have these individual cores called C0 to C3. They are each attached with a 2-level cache hierarchy. And then, as I explained before, there's a level 3 cache that spans all, in this case, 4 cores. And this is then connected through a memory interface on die. Today it's on die to the actual memory banks in your computer. Now the first task it will be find out how many cores your laptop has and paste it to the Etherpad. Okay? So find out again the model if you don't have it anymore. So there's 4 cores. Unfortunately I can yeah, CPU 4 is enough. CPU is 12. All right.
Somebody checks.
Yeah, but that's totally fine. I mean, okay, there's one.
You can log into our class and then you get CPU.
Yeah. Okay. Okay, so just continue pasting. Most of the people have 4 cores apparently. Why? What do you mean why? This is for note taking. This is the chat. Well, anyway. Yeah, because you're poor. Okay. Okay, some people paste here threads, some CPUs. I guess you mostly used LS CPU. At least it looks like it. And this is on enough, exactly. So then I will show you how many cores I have. And I do it differently. So this is basically an entry in the Linux online file system. Yes? And one thing I wanted to show you is, I would like you to look at this as well. So you can just call less and then /proc CPU info. And then, why don't we just do something like this? It's called core ID. Yeah. Okay. So you can also check here. Exactly. This is what I wanted to have. What's it called? Core ID. And I would love if you could just do this on your laptop. For those of you who don't know grep, just take it as is. This is of no importance. This is just a tool. If you want to learn it, I can show you how to use it, but there's also great material online. So this is quite strange. Who has similar output? Most of the people, right? So who has 0, 1, 2, 3, 4, etc.? Is there anyone that has like a ramp of numbers? You guys do? Okay. Anyone else? So the rest of the people, I guess, have such a pattern. Is that correct? All good. So why? Question is why. This is important. Yes. What is hyperthreading? Yes. Yes. Did everybody hear that? Whoa. Okay. I don't want to see any red sticky notes then, okay? I didn't understand what you said. So if you didn't, so this is a special feature of a lot of hardware pieces. It's called hyperthreading. It's a very neat trick, mostly pioneered by Intel. Other chip vendors actually have adopted it. There's actually not many chip vendors else today. And what this basically means is that physically you have 2 cores, but your operating system sees 4. And they do this with a special trick, because the performance that you get out is not as if you would have, in my case, 4 cores. So this is simply something to take into account because we will do measurements. And then people will ask, Why is it a factor of 2? It should be a factor of 4. And this is one of the reasons. Okay, because effectively you split up the work that one core can do, in a sense that the hardware will allow the operating system to shuffle in more instructions, and it simply has a capability to put in more instructions if possible. Problem is you only have a physical core, so it can only do some amount of work. Okay, so it really depends on the application. In the HPC arena, typically hyperthreading is switched off because people think that they will not game. In the industry, where money sometimes matters, sometimes not, people actually switch it on. It depends on your context. For a laptop, it's totally fine. Okay? All right, so enough of the chatting. Let's do some work. All right, let me pull up my notes. So again, we are here, and we want to still calculate the total power that is consumed. Yes. So power total. We leave this test for legacy reasons, and we want to sum up sequentially. So as again, we should start with a reference, because even if we would not have the sequential case, there is nothing we can compare to and see if our implementation actually gives us a benefit. Okay, so basically the situation for Lola is that she wants to compare the total power consumption of the entire institute between two distinct points in time. All right, so what we have to do, we again create a vector of device t, and this is our first time point, whatever you want to call it. We just do a blunt copy, and then we want to have a second time point, which start out with a copy, and then we do an update. So the update function that I use here basically does simulate as if some time would pass, and the actual numbers inside this device info vector would change. So still, this is again the situation where we have this device underscore t objects, and we would need to deal with it. So to start off, we don't want to start straight away with summing up something. We first want to start with calculating the difference. Okay, so we want to compare basically, or just simply subtract the entities inside first time point minus the ones of second time point. Now I decided to do it the STL way. Okay, for those of you who don't understand, we can briefly discuss this. I just wanted to expose you to some STL programming. For the other ones, I feel free to look it up. There is a nice web page called cppreference.org or com. CP reference. I can only suggest have a look at it. It explains, or it has a nice reference of the standard library, including examples. That they are not always nicely fit and help you, but most of the time, which I like about this page. Okay, we again have our repeats, and then we use a standard transform. What? First time point begin. So we first have to define the range, and then we have to tell it what to use as the second operand. Ah yeah, and I of course forgot something. I forgot to prepare this. Yeah, I have to prepare the result and do it like this, and then what we'll do, we use a functor that comes with the STL, which is called minus. So let me pull this out, let people actually see what's going on, and then I need to do the includes that are missing. So this is coming back to the notion no raw for loops. This is what I just did. I could have just written a for loop and just had delta square bracket I equals first time point square bracket I minus second time point square bracket I. It's basically doing just this. Who has no idea what this transform call does? Just be honest. Wow. Okay, where to start? So let me think. So a standard transform basically is a function call, a templated one that allows you to transform input vectors to an output vector. The first three arguments are the inputs. The fourth argument is the output. And the last argument is basically what's to be done. We could just as well write something like this if you're familiar with lambdas. Who is familiar with lambdas? Who has never heard of lambdas? That's what I thought. So a lambda function is a local unnamed function that I just write inside the source code. In Python, they have to be introduced with the lambda keyword, and this whole business about lambda is very important to computer scientists because it was shown a long time ago that with these so-called lambda syntax, you can create programs that are Turing complete, that can solve any problem, basically. Anyway, C++ has them, Java has them, Python has them. This is simply a function that I define inside the code, which has no name. Right? Otherwise, I would always say void do something here, and then implement some function text, right? And here I just say take whatever, take nothing from the outside, take these arguments I will continue, and then I will add an implementation. This is what's called a lambda function. And what I had there before, I should actually have it. You will see hopefully in a minute what this is to be done. So this is more or less the modern replacement of a functor. Who knows what a functor or a function object is? Guys. A functor is a well, okay. The other, so what standard minus is, because see, this is what always happens, and this is totally okay. I had, what did I have? This. Okay, this is a functor, which is inside the standard library. A functor, I could also write it like this. Again, I'm using a struct to make my life easy. A functor implements the operator bracket and not more. This is the operator bracket. Okay, so I will show you in a minute how to use it. And from now on, I can simply copy what is in here. So this is at the very heart of C++. I did something wrong right here. This is the basement of the STL, of the standard template library. So this is simple and a function object. So you see this is an object, but it doesn't have any fields. It does only have one member function, which provides some functionality. Standard minus device T does exactly the same. You can look it up. Why don't we just look it up? I mean, I'd rather teach you some good practices in C++ than dive too much into, well, we should dive too much into parallel. Minus, I think. So there is standard minus. So this is C++ tpp-reference.com. This is the minus operator. And let's see if they have an implementation example. There you go. This is how it's, well, this is the C++ 11 way to implement it, but yeah. So you take a type, 2 arguments of a type, you just compute minus and return the value. That's it. And if you compare this to what I've just written, except for the reference, which is okay here, this is the same. So let's use my minus. So the standard library is basically based upon this model. That you have functions that you can provide a function object with, and the functions do nothing more than loop through the input array and apply this operator one by one. Just apply it for every item. And the standard transform is a binary operation basically. You have to provide it with a range, so an iterator range basically for the first vector. With this, it knows the length, how long to loop. Then you have, because it's a more or less a binary operation, the second argument. This is, it takes every item from here, makes it the first argument. Every item here is a second argument, and this is the result. And then you tell it what actually to do. Okay. So this is standard transform. Yes.
What happens if the second object is smaller than the first?
Then you get a segmentation fault. It will not. Does it check? I don't know. I think it does not check. No, it should not. Let's see again. So this is one of my favorite resources, standard transform. So you see there are 2 incarnations. One with the one we used is the bottom one, and then there's also the top one, where you simply have one vector that you want to apply an operation on and then put it into another. Okay, there's 2 inputs, the first and the last, and then the actual target.
Just a segmentation fault, but you get wasted error.
Yeah.
Exception.
It raises an error. Yes. Okay.
That is much nicer than just seg faulting, because
Yes.
you can actually catch that exception.
Yeah.
If it happens, and then you break your program, or if you think that could happen once in a while, continue in the error.
No.
The STL throws error.
Yes. Okay, so this is an algorithm. I think I forgot to add this, and minus is in functions or something. And then minus is, let me check where minus is. So I'm doing this here in functional. So so that you see the workflow. A good IDE should actually tell you. I made this CMake for now, not so fancy, not to overwhelm you. It's just an editor today.
I think, can we see your lines again?
Yes, it's right here.
There.
Yeah. So I'm basically doing what should be done. I hope it compiles. I didn't even compile it. Command attempted to use mini power. No. What did I do wrong? No match for call. This is the downside of it, I have to say. I think I need to inherit from binary operator. So that's why let's stick to standard minus first. Because I don't want to debug it right now, since this was quite a detour. Standard minus device T. Whoa. Yeah. Device T, template argument 1 is invalid. Ah, of course. Forgot the namespace. Of course. What else? Does not name a type. Of course, because I forgot the namespace. This was probably the reason. This was the reason why it didn't work. And then repeats is not defined. Okay, that's handleable. Static int repeats equals 10. I didn't include timing, so, and there you go. And now it takes time, it takes time, it takes time. And how? 5 seconds. Okay. Let me check again. So the overall timing that I get from the test outputs is including these copies. So I might contemplate adding some timing again. Okay. So let's try to do this in parallel. But I think we have 10 minutes to go, so it will be hard to actually finish something. We could start. Shall I start, or should we do a feedback round? We can also do this. Yeah, because now we only have 10 minutes, and then masses of people will come in to see the talk. At least that's what Isabel told me. Okay, good. Then I'm sorry about this, but I hope that I triggered your curiosity a little bit with standard transform to have a look at this and how to use these algorithms. Because I personally think if you're literate in this, it can help make your code more readable. Because if you it's a matter of discussion, but if you're used to this, I immediately know what a transform does. And if somebody just puts in all these for loops and everything, it can look messy. So there's always a trade-off. Okay. All right. Good. Then I would do a feedback round. Again, take the green and the red sticky note. Please write down something you liked and something you didn't like, or write down on the green sticky note something you learned, something you had fun with, something you found curious. And on the red sticky note, please put down what you didn't like, what you want me to improve, or something on the matter. And then just let's have a break already now, and then relax for the day and continue tomorrow. So at least the good point is we have a sequential version of the algorithm working. Actually, thinking about it, I didn't put any test assertions in. If it does actually work. So let's see. Okay. Let's see if it still runs. Ooh, what did I do? Okay, it runs through. So what I just added some test assertions at the end, which we should have started with actually before adding the implementation of the transform, if we would be good developers. But yeah, I was just too distracted with the standard transform. Okay, so again, why don't we just, as I said, just close at this point, put your sticky notes on the door, or just give them to me so I can put them on the Etherpad, and then we're done for the day and continue tomorrow with parallelizing this task. What I basically want to do, I mean, you can also feel free to pass the material tonight if you like. I want first to start with plain threads, show you how it's done, and then tell you to never do it again if you don't have to. And then at the end, we will use a library that does the parallelization for us, which is the approach I would recommend to you to always start with. And then if you really have to, use plain threads.